Hello everyone, and this week's lab is going to be torque. And torque, what is a torque? A torque is a twist or turn that tends to produce rotation. Now it tends to produce rotation, so just like we talked about in the previous lab, tends to doesn't mean always does. A torque can still be applied that doesn't end up in any rotation. Uh, Applications are found in many different tools around the home. We have a torque wrench, we have an air gun, we have an open-end adjustable wrench, and we have a spigot. As seen in the previous slide, the definition of torque is defined as the tendency to produce a change in rotational motion. Here we have somebody turning a pipe wrench. Here we have a drill. A drill will apply torque and cut through the wood. The pipe wrench will turn the socket. Torque is determined by three factors: the magnitude of the applied force, the direction of the applied force, and the location of the applied force. Here we have a 40 Newton force produces twice as torque as does the 20 Newton force. So here you have a distance, and so the magnitude of if the magnitude doubles, then so does the torque. Each of the 20 Newton forces has a different torque due to the direction of the force. The forces near the end of the wrench have greater torques. So as you'll see, there's a reason for that when we get into the mathematics for it. Units for torque. Torque is proportional to the magnitude of force to the distance r from the axis. Thus, a tentative formula might be T equals Fr sine theta, where F is the force applied, R is the distance between the center of rotation and the location of the applied force, and theta is the angle between the arm and the force. Units, of course, are Newton meters. So here we have 6 centimeters times Newton, so you change 6 meters to meters and multiply it times 40 Newtons. And that gives you 24 Newton meters, and that is clockwise. All right, here, just in this picture, theta is 90 degrees. So if Fr sine theta, theta is 90, so sine of 90 is 1, and so it just comes up as Fr. Direction of torque. Torque is a vector quantity that has a direction as well as a magnitude. Turning the handle of a screwdriver clockwise and then clockwise will advance the screw inward and outward. You've always heard the righty-tighty, lefty-loosey. There's a reason for that. Sign convention for torque. By convention, counterclockwise torques are positive and clockwise are negative. Positive torques, counterclockwise out of the page. Negative torques, into the page. Example 1, we have an 80 Newton force that acts at the end of a 12 centimeter wrench as shown. Find the torque. Extend the line of action. Okay, line of action is the line of which the force is acting. You can extend it in either direction forever, and that is called your line of action. Now calculate D. In this picture on the left, what's called the moment arm, we are going to refer to that as the lever arm. And then there it says R. However, R we are going to keep as what would be the 12 centimeter arm. That is your R. And then what here is labeled R, we're going to call D. And that's the way it's done up in the lab handout. So D equals 12 centimeters times sine 60, which is 10.4 centimeters. So the torque is going to be F times D, which is your 80 Newton force, times 0.104 meters. And in the picture to the right is a bit confusing, using R to represent the moment arm. In our left handout, we will use D to represent the lever arm. Calculating the resultant torque. Read the problem, draw a picture, and then label a rough figure. Draw a free body diagram showing all forces, distances, and axis of rotation. This in the lab we're going to call an extended free body diagram, because instead of just a point, you're going to have to actually draw a picture. Extend the lines of action for each force. Calculate the lever arms if necessary. Then calculate the torques due to each with using the convention, where it's counterclockwise or clockwise. And then the resultant torque is the sum of all individual torques. Okay, find the resultant torque about A in the arrangement below. So it looks like we have 1, 2, 3 forces, so we're going to have 3 torques. Find the torque due to each force. Consider a 20 Newton force first. Okay, so 20 Newton force. D is going to equal 4, which is the distance, times sine 30, which is going to be 2 meters. Then FD sine 30 is going to end up being 40 Newton meters. And it is negative because it's going to want to make it go counterclockwise, or go clockwise. Okay, then let's look at the 30 Newton force. So it's going to be, your D is going to be 8 meters times sine 30, which is 4 meters. And FD sine 30 is going to be 120 Newton meters clockwise. So that's also negative. Now if we consider the torque to the 40 Newton force, that is going to be 2 meters times sine 90 degrees. Sine 90 is 1, so it's going to be 2 times 1 is 2, so it's 2 meters, times the force of 40 newtons is 80 Newton meters. Counterclockwise, so it's positive. So to find the resultant, we're going to just add them all together, which is negative 80, which is going to be it's going to be clockwise, which is negative. Summary of the resultant torque. Read, draw, and label a rough figure. Draw a free body diagram showing all forces and axis of rotation. Extend the lines of action. That's really important to do. Calculate the lever arms if necessary. That's your R sine theta. Calculate the torques due to each individual force, affixing the proper sign of clockwise or counterclockwise. And the resultant is the sum of all torques. One thing I want to mention is what is the net torque? Net torque is the addition of all the torques. And if it's positive, it'll go counterclockwise. If it's negative, it'll go clockwise. And if the zero net torque, then it'll be stable. Let's see here, equipment. We will be using the force probe. We'll be using the force probe to find out what the forces are at a length. There will be a long wood block with several rotation points drilled through it at equal distances. And we'll be using a protractor to determine angles. So you're going to use a protractor again. And something to think about. In the past, we talked about what it means to have zero net force. What about zero net torque? I just answered that for you. How would a beam, or how would we find the force necessary to balance this beam? So if you had that, what would F be? That was kind of going to be important to know. And that is all. So we will